As you know, materials get bigger when they're warmer, and they get smaller when they're cooler. They expand when they're hot, they contract when they're cold. This is true of all materials, but it is an issue if you're thinking about designing structures like bridges or buildings. If you think back to structures class, when we looked at support conditions for beams, you might remember that we talked about roller connections and how we often put a pinned connection under one end of a beam and a roller or a rocker under the other end of the beam. And mostly, it's because of thermal expansion due to heating. So, for example, if you have a bridge beam and it's 300 feet long, and you install that bridge beam when it's 35 degrees Fahrenheit, so wintertime. In the summer, let's say you're in July or August and the temperature gets up to 90 degrees Fahrenheit, that bridge beam is going to be 1.2 inches longer than it was when you installed it. Well, that's considerable. Now, if you've put a roller connection under one end, then no problem, it just expands. If, however, you've put a fixed connection on each end, and maybe you put the ends of your bridge in between abutments like this picture, then as this beam gets longer, it gets compressed and you get compressive stress building up inside that beam. And if it's enough, you might even get the thing buckling. And we see that with railroad tracks sometimes. We see thermal expansion applied in joints in concrete, like concrete sidewalks. There's a thing called an expansion joint that accounts for thermal expansion. Now that's different from a construction joint or a contraction joint. There are three different kinds of joints. A construction joint is the joint, and we don't see that here. A construction joint is where you've poured two different panels of concrete at two different times, and so there's just an abrupt edge where the two come together. A control joint is a zone where you cut a crack. Let me back up. So you use one of those concrete edging tools to cut a groove in the concrete so that when the concrete cracks, and it will, you have given it a place where it will preferentially crack first. You don't want the slab that people walk on to crack. You want cracks to form in that little groove where you intend it to form. And you will notice that in a well-designed sidewalk pour, these chunks of sidewalk tend to be almost square in between those control joints. The ratio needs to be no more than 1.5 times as long as it is wide. So construction, where two slabs come together. Control, where we're trying to direct the cracking that will inevitably happen. And then an expansion joint is the third kind, and that is, backing up again, that is a joint that has this expandable material in there. Sometimes it's oakum, but I think there's a higher tech kind of material we use now. And that flexible material is specified by ASTM, American Society of Testing and Materials. And that is to accommodate expansion when the thing gets hot and expands. Now we can use contraction as well. In manufacturing, there is a class of fit called an interference fit, where the thing that goes in, like a shaft or a pin, is actually bigger than the hole it fits into. How is this possible? Well, with a light interference fit, a press fit. That's called get a bigger hammer by some people, or get a hydraulic press where you can just press the thing in. But in a case like this, where let's say you've got a big machine with a big machine shaft and it has a big bearing that's supposed to fit onto it, what manufacturers do is they submerge the shaft in liquid nitrogen for about 24 hours. And as you probably know, in order to become liquid, nitrogen has to go down to a very, very cold temperature. So they're putting this shaft in liquid nitrogen and chilling it. And when it gets very cold, it gets smaller. Then they lift this frozen component out and put the bearing race onto the shaft, and then just let the whole thing come back to room temperature. This shaft will expand to its original size, and it will press against the inside of that bearing. It will be a shrink fit, and those two pieces of metal will essentially become one piece of metal, and you are not getting them apart again unless you use machining. Well, we can also apply thermal expansion when we put metal tires on wooden wagon wheels, and this was the way tires were put on in the 19th century. So this band around here is iron. This was before steel making processes got sophisticated like they are now. So you take a piece of iron flat bar and roll it in a circle and weld the ends to make a circular tire. And you make the circular tire smaller in diameter than the wood wheel it's supposed to drop onto. Then you put that welded circular tire into a fire in a forge, and you get it red hot. And what happens? It gets bigger. So now it was smaller than the wheel. Now it's slightly bigger than the wheel. And you lay the wooden wheel down flat on the floor. You drop that very hot tire onto it, and then real fast as possible, about 6 people with blacksmith tongs, these long things, pick up that wheel and the tire, and by now the wood is starting to smoke because that tire is real hot and it's starting to burn, so you got to move fast. So you pick up this wheel, you race over to this trough with cold water in it, and you plunge the wheel and the tire into the trough. And it's very exciting. Steam boils up from the trough, and there's lots of sizzling noises. And the tire cools down immediately and shrinks onto the wooden wheel. So now it's gripping that wheel because the tire was originally smaller than the wheel, as you recall. Well, thermal expansion is a factor in sea level rise as well. And I'm sure you're aware that as sea level rises, places like South Florida are beginning to see inundation from the ocean, and that will grow as sea level continues to rise. And a number of scientists and geographers are beginning to use GIS and other kinds of software to make models that predict how far will the water come in depending on how many inches or feet the water rises. So why is this happening? A lot of people think the sea level is rising because the Arctic ice up at the North Pole is melting. You know, up there the water is getting warmer, and so the ice is melting. However, that's not what's causing it. Think about having a glass of ice water. You have the water in the glass, you drop the ice cubes in. Do the ice cubes make the water overflow as they melt? No, they don't. Whatever height that water is with the water in the cubes, it just stays that high because the ice is already in there. And likewise with polar ice up at the North Pole. What is causing sea level rise is good old thermal expansion. And we have lots of data on this, so we're quite certain that's what it is. The ocean temperature is rising. The oceans are getting warmer year by year. And as they get warmer, the water literally expands, and there's no place for it to go but up. So it goes up. Now, we do know that terrestrial glaciers, glaciers on land, are beginning to melt. Glaciers, there's some worry about glaciers on Greenland, which are melting. And if those glaciers actually slide into the sea, or their melting water flows into the sea, or the same thing happens in Antarctica, where there are some big glaciers that are beginning to melt and slide into the sea, those two phenomena will contribute some water to sea level rise. But for now, the primary cause is thermal expansion. You also might have used thermal expansion when you've loosened a jar lid. You ever had one that's stuck and you run it under hot water and then it loosens up and you can take it off? I used to think that we were doing that because there was sticky food stuck under the lid and we were kind of loosening it, like if it was jam, you were melting the jam. Turns out that's not what is happening. Every material expands at a different rate when heated to the same amount of temperature. That's called the coefficient of thermal expansion, which we're going to look at next. Well, it turns out that steel, which is a jar lid, steel has a much higher coefficient of thermal expansion than does glass. And if you put a glass jar with a metal lid under hot water, for every degree of temperature and every inch of diameter, the steel lid is going to expand about 40% more than the glass does. So it gets bigger, more bigger, it enlarges more than the glass does. We have charts that look at what is the rate at which various materials expand, and these rates have been established by testing in the lab. So here is steel, our jar lid. There's its coefficient. Here is glass. There's its coefficient. You can see whatever this means, we don't know yet, but it is a lower number. 4.4 is a lower number than 6.5, whatever that is talking about. So we are going to, we'll stop here, and in the next video we'll look at what these numbers mean, and more particularly, how can you apply those numbers to figure out how much something will expand.